In our previous lesson in this series, we looked at the bonding that takes place in covalent compounds. We also looked at how to name and how to write the formulas for non-organic covalent compounds. Today we're going to continue with that, but transition to our understanding of ionic bonding and ionic nomenclature. And nomenclature is a naming system. And in the last lesson, we were working on bonding and nomenclature for covalent compounds. Today we're looking at, or beginning to look at, ionic compounds. And at the beginning of the previous lesson, we looked briefly at what metals and nonmetals do. In the last lesson, we were talking about covalent compounds primarily. And in covalent compounds, you have nothing but nonmetals bonding with nonmetals. Now, when I say nothing but, there's always exceptions to that. So, when I say nonmetals bonding with nonmetals is where you get covalent bonding, that's 99% true. Occasionally, there are exceptions to that, okay? The same is true with ionic compounds when we're talking about metals bonding with nonmetals. That 99% of the time, when it's a metal bonding with a nonmetal, you get an ionic compound. That means that there are some exceptions, okay? And there are some ionic compounds that don't have any metals at all, but we'll get to that when we get to that. That's a different sort of category at the moment. So, this stair step here on your periodic table is the dividing line between metals which are up here, nonmetals which are up here, and metals which are down here. Okay? And if I bond a metal anywhere on this side of the periodic table with any one of these nonmetals anywhere over here, we're going to assume, for the moment at least, that we're always going to get an ionic compound. And in ionic compounds, the metals tend to give up electrons, nonmetals tend to gain them, and the way we think about it is that the electrons from the metals tend to go to the nonmetals. Okay? That's where we're going to approach this problem here, or these problems like this. All right? So, since we spent quite a bit of time already in the previous unit and already in this unit writing orbital notation, let's write the orbital notation for two elements. Write the orbital notation for sodium and for sulfur. Write orbital notations for sodium and for sulfur, and we'll use that to figure out how this ionic bonding occurs. Alright, so here is the orbital notation that I've written for sodium and sulfur. Now, you may notice that I've written one electron in red pen there, because what's going to happen is, when we are combining a metal like sodium, sodium is on the left-hand side of the periodic table, this stair step dividing metals and nonmetals, and sodium's over here. So it wants to give up electrons. So it wants to get rid of that electron, and when you get rid of that electron, what remains is a full outer energy level. Okay, so we have a valence level that's now full, what remains anyway. Okay, so this electron here in sodium is going to want to leave, and when it leaves, it actually has somewhere to go. In the previous unit, we treated the electrons as if they just kind of left and went nowhere. Well, they do go somewhere. And the way we think about it here in this class is that they go to the nonmetal. And the result is that sodium now has lost an electron. So that electron left here. And now it's going to here. And since sodium originally had 11 protons and 11 electrons, protons are positive, electrons are negative, they cancel each other out. Sodium, the atom, was neutral. Now it doesn't have as many electrons. It has one less electrons. It has one more proton than electrons. Protons are positive, electrons are negative, so now this has a positive charge overall. Okay? Sodium now has a negative charge, but it's not where it needs to be yet because it wants to have a full outer energy level. How many electrons do atoms tend to want to have in their outermost or valence energy level? 8. We call that the Octet Rule. Excuse me. And so Sulfur needs one more electron out here to have 8. It's got 2, 4, 6, 7 electrons right now, but it wants to have 8. So the question that was posed to me was, why doesn't the spin of the electron matter? Because I took one out of here that was spinning up and put it down here and it's spinning down. Well, spinning is relative. Okay, it's relative to where you are. Okay, if you're in space, outer space, for instance, what is up? You don't know, because it really depends on your direction, right? And what's up for you is down for somebody else. And it's kind of the same thing with electrons. All right, so what's up here only is relative to what is right next to it. Okay, got that? All right. So the way we deal with that then, or what happens then is sodium. There's going to need to be another sodium to satisfy the electrons that sulfur wants to have. So I have another sodium here, and this electron here is going to want to leave sodium, as that one did. And you can go up here and join up with the sulfur, giving that sulfur a 2 negative charge. Let me get rid of that electron in sodium's orbital notation structure. Okay. And now this sodium has a 1 plus charge. Yeah, even though in the last unit we treated these electrons as either coming in from nowhere or going out to anywhere, they don't really go to nowhere or come from anywhere, okay? They actually are coming from someplace. And that's the way I want you to think about it. Now that we're in the unit about bonding, that's what I want you to think about, okay?
So the sodium has...
Metals always give to nonmetals. Now, let's look at this same sort of idea, this concept of moving electrons around and what results. Now, you got to understand this. Whenever you're looking at a formula, you've got to look at where those elements come from, okay, on the periodic table. Metals are going to be over here, nonmetals are over here. If you have metals bonded with nonmetals, you've got to look at that and say, oh, that's ionic. You with me? Because this is important. When you look at a formula, you first need to determine what kind of formula it is. If I have nonmetals bonded with other nonmetals, you've got to say in your head right then, that's covalent. When you see metals bonded with nonmetals, you've got to in your head say right then, that's ionic. Okay, now despite me saying this and saying how important it is and going over it and over it and over it, I can guarantee you somebody on this, in this class, on the next test, is going to get it wrong. Because somebody in this class, on the last test, got it wrong. Okay? When I asked you to do stuff that was covalent, they got it wrong. Okay? It happens. All right? So you've got to know what covalent and ionic it is. All right? You've got to be able to figure that out. So please don't, let your brain go into, sleep mode here. All right? Focus on what we're doing. All right, so we're going to look at this in terms of electron dot formulas now, okay? So sodium originally had 1 electron dot in its outer energy level. Okay, so I'm going to put 1 electron dot here. And if I was using sulfur and its electron dots, as if this didn't exist, I would have 2, 4, 5, 6 electrons. So we're ignoring the 2 red ones we moved in from the sodiums. So we have 1, 2, 3, 4, 5, 6 electrons in the valence level of sulfur. We said that sodium, which is a metal, and as all metals do, tend to give up electrons. So we're going to take this electron right here, and we're going to give it up and take it down here and put it into sodium's electron dot formula. Okay? I'm sorry, sulfur's electron dot formula. So it's going to go right there, and this little dot's going to disappear up here. Okay? As a result, this sodium now has a 1 plus charge, and we've given this sulfur a 1 negative charge. Okay? But we don't want to have anybody misunderstand. This negative charge applies to the whole sulfur, not to just 1 electron somewhere nearby or this side of it or something. So I want to put a bracket around this to show that it applies to the whole structure. Okay? Now, it's not finished yet because sulfur wants to have 8 electrons. Now, what you got to understand about sodium is, even though we don't show any electrons here, you have to, in your mind, know that this is the actual structure. So even though we don't show any electron dots in the electron dot formula of a sodium ion, what is really happening is we're losing one from the outer energy level and leaving a full valence level behind. You've got to know that. Okay? So you have to make an inference here. Okay? Anybody who's doing stuff in chemistry ought to know this is implied. And you ought to infer that there are, what remains then is an outer energy level that's full. Okay. So then we need another electron to fill up the valence level of this sulfur here. And we're going to use another sodium to get there. So here's sodium with its one electron dot. We're going to move that electron dot up here. And now we've got a full valence level for sulfur. Sulfur now has a 2 negative charge. And sodium, once I get rid of this electron dot, because it now has 10 electrons and 11 protons. Protons are positive, electrons are negative. And since it has more protons, one more proton than electrons, it's going to have a 1 plus charge. And so this would be the electron dot formula for a combination of sodium ions and a sulfur ion. Okay? Now, there's another way to go about figuring out how to balance these formulas. If I were to write this formula just from this, I want to write the element with the lowest electronegativity first. Sulfur's right here, sodium's right here. Sodium has a much lower electronegativity than sulfur does, so we're going to write it first in a subscript 2 followed by capital S. There's the formula for sodium sulfide. 2 sodiums and 1 sulfur. Now notice when I said the name there, I did not use those prefixes. Those prefixes that we learned in the previous lesson, okay, di, tri, and all of that. Let's see if I can put this up for you. Okay, all these prefixes here. We learned those only apply to covalent compounds. You see it says covalent compounds on the screen. It does not apply to ionic compounds. So when we're doing ionic compounds, there's a different naming system, and it doesn't include any prefixes. So when we name this, we call this sodium sulfide. Okay, just simply sodium sulfide. Or sodium sulfide. Okay? This is the American way of saying it, or writing it. This is the rest of the world's way of writing it. Okay? Huh? No, well, Russia too. Anywhere else in the world does it like this. Almost anywhere else in the world does it like that. Okay, now, let's look at another way to go about writing the proper kind of balance formula here, okay? There is another way to do this. That actually shortens up some of this, and eventually we're going to get completely away from all this and get to this other way of doing it, okay? So sodium had we can imply from the periodic table that sodium had 1 electron in its outermost energy level. Do you agree with that? Because it's in this first row of the periodic table. All these elements in this column have 1 electron in their valence levels. So in order for it to get to a full outer energy level that has 8 electrons, following that octet rule, it could lose 1, and just by losing 1, it already has the orbital notation, or electron structure anyway, of neon, which has 8 electrons. Okay? So by getting rid of 1, we know that we can follow that octet rule, but if we get rid of 1 electron, then sodium is going to have a 1 plus charge. So we're inferring a 1 plus charge on the sodium. Before we do anything, we're going to go ahead and infer it's going to have a 1 plus charge. Okay? If we go over here to sulfur, it's right here. I can infer from its position on the periodic table that it has 1, 2, 3, 4, 5, 6 electrons in its outermost energy level. 2s electrons represented by the position of sodium and magnesium, and 4 here represented by aluminum, silicon, phosphorus, and sulfur. So 6 electrons in its valence level, in its outermost energy level. And if I just add 2 more, represented by the position of chlorine and argon, then sulfur will have an outer energy level that has 8 electrons. Okay, it'll have the same electron structure as argon. If I add 2 electrons to sulfur, it's going to have a 2 negative charge. So I can infer that sulfur, when it is completely satisfied with electrons, will have a 2 negative charge. You understand what I did? I'm jumping ahead. I'm saying, okay, I know all this is going to happen, and if all this happens, then sodium's going to have a 1 plus charge, and sulfur's going to have a 2 negative charge. That's what I wrote down here. We've been doing this enough now that you should be able to make that jump in logic. That when we get to the electron structure that sodium wants to have and sulfur wants to have, sodium will have a 1 plus charge, and sulfur will have a 2 negative charge. You with me? Okay. If that's the case, what we really need is a formula for a combination of sodium and sulfur that has a 0 charge overall. It has a neutral charge. We need a balance of sodiums and sulfurs so the charge on the overall compound is wiped out. It's 0. It's eliminated. Okay? So sodium has a 1 plus charge and sulfur has a 2 negative charge. Okay? And what we need is to be able to add sodium and sulfur together in a way that gives us a 0 charge overall. So we need some coefficients out here. All right? So if I put a coefficient of 2 here, that's going to make the math work out. Does that make sense? Because by doing that, then 2 times a 1 plus gives me a 2 plus, and a 2 plus plus a 2 negative gives me a 0. You with me? Well, if that's the case, that tells us that we need 2 sodiums to balance the charge of 2 negative on the sulfur. And as a result of all that, if we put all that together, we're going to get a formula where we have 2 sodiums. And the way we show 2 sodiums being bonded to something else is use a subscript here, subscript 2. That's what that lower right-hand position, subscript position means. It means I have 2 sodiums bonded to each other and to something else, possibly, if I put something else here. And if I put a sulfur here, it means we're bonding those 2 sodiums to a sulfur. Okay? And so we can get the correct formula for sodium sulfide using this process. I can use all of this, or I can use this. Okay? All right. Let's give you guys a chance to try one out now. So I want you guys to do this problem. Okay? So you're going to be using orbital notation like this, electron dot formulas like this, and then finally using the ion symbols, and these are ion symbols right here. Okay? Na plus is an ion symbol, S2 negative is an ion symbol, and use all 3 of those to get to the correct formula and name for a compound that has magnesium and phosphorus in it. Okay, correctly balanced compound name and formula for a combination of magnesium and phosphorus. All right, so if you're going to write the orbital notation, let's start with orbital notation here. Okay, so here's the orbital notation for magnesium. Now I've written these 2 electron arrows over here, and I know those don't look like arrows, like 1s and L's or something, but it's like half arrows because it just speeds it up. 2 electron arrows in the valence level, the highest energy level for magnesium, and I made them in red because we're going to do something with those. And then phosphorus is this, and phosphorus has 2, 3, 4, 5 electrons in the valence level. Now magnesium, the metal, wants to give up all the electrons it has in the valence level. Okay, since it wants to give them up, if I move them down here, okay, then magnesium has gotten rid of all the electrons it wants to get rid of in its valence level. White out those things. Or what?
But then there's one left.
You're right. So this has a 2+ charge now because I've gotten rid of 2 electrons. Magnesium had an equal number of protons and electrons. Now it doesn't. It has 2 more protons than electrons. Protons are positive, so therefore it has a 2+ charge, or it has 2 more protons which are positive. Electrons are negative, so it has 2 more positive charges than negative charges. Phosphorus has 2 more negative charges, but it needs 1 more over here. Okay? The only way to get more electrons is from magnesium. So let's write out another magnesium here. And we're going to move this electron up here. Okay? And now this magnesium has lost 1 electron, but it still wants to get rid of another one. Okay? So this phosphorus now has 3 electrons, 3 more electrons than protons. So it's going to have a 3 negative charge. Okay? Electrons are negative, protons are positive. If you've got 3 more negatively charged particles than positively charged particles, you have a 3 negative charge overall. Magnesium has a 1+ charge, but it still needs to get rid of an electron. And so the way you get where you move an electron when you get rid of an electron is to a phosphorus. And so here's another electron moving down here to phosphorus.
Put another phosphorus in.
Okay. And so this electron's gone now. We're going to put that phosphorus down into that electron down in the phosphorus structure. Okay. Now this magnesium's gotten rid of 2 electrons. It has a 2+ charge. Phosphorus is a 1 negative charge, but it needs 2 more electrons. Well, where do you get electrons from in this structure? Magnesium. And so this magnesium wants to get rid of these 2 electrons here. Until you keep going until everything is worked out. And so this magnesium has lost 2 electrons. It has a 2+ charge. This phosphorus has gained 3 electrons. It's 3 negative. Okay, and so everything's worked out now. Okay? All right, now, using electron dots then, magnesium had 2 electron dots to start with, and phosphorus had 5. 1, 2, 3, 4, and 5. So if I move these 2 electrons over here to the phosphorus, so I put an electron there and an electron there. And magnesium, we're going to show its 2 electrons as disappearing or going because I'm moving them away. All right. That gives this magnesium now a 2 positive charge. And the phosphorus still needs an electron. And where do you get electrons from? Magnesium. So here's magnesium with 2 electron dots. And I can move one of these electron dots up here. Okay, now phosphorus has 3 electrons, extra electrons. That's what it wanted. That's a 3 negative charge. Oh, 3 negative charge. Let's get rid of that 1 or whatever I did over there. Not sure what that was supposed to be about. Okay, and then this 3 negative charge applies to the whole phosphorus. Okay. Now then, this magnesium still needs to get rid of an electron. Well, you get rid of an electron by sending it over to a phosphorus. Phosphorus had 5 electron dots. Move this electron over here, giving phosphorus an extra electron. Now this magnesium has lost both the electrons it wants to give away or loan away or whatever. So now this magnesium has a 2+ charge. But phosphorus needs 2 more electrons. Well, where do you get electrons from? Magnesium. So here's 2 more electrons for this phosphorus. Move these 2 electrons here. 1 there. 1 here. And now this phosphorus has 3 extra electrons. So it has a 3 negative charge. This magnesium is going to lose both its, or did lose both of its electrons. I haven't marked it yet that way. So now has 2 2+ charges. Or it has a 2+ charge. 3 magnesiums with 2+ charges, 2 phosphoruses or phosphori, I suppose, with a 3 negative charge. So using this system here with orbital notation and this system here with electron dots, we came up with a formula that was 3 magnesiums and 2 phosphoruses or phosphori. Okay? Now let's look at how we might do this regarding charges. Well, if we look at magnesium's position on the periodic table, it's in column number 2, and you should by now be able to infer that it wants to get rid of 2 electrons because of where it is. It has 2 electrons in its outermost energy level, represented by the positions of sodium and magnesium. If I get rid of 2 electrons, it's going to have the same electron structure as neon. Neon is a noble gas with 8 electrons in the valence level. And if I get rid of 2 electrons, that's going to give magnesium an inferred charge of 2+. Phosphorus is right here. It's easier for it to gain 3 electrons and be like argon, or have the electron structure of argon. So we can infer a charge on that phosphorus of 3 negative. Okay? So if we have a 2+ charge on the magnesium and a 3 negative charge on the phosphorus, and what we want overall is a 0 charge, well, if I have 2 of these 2+ charges, and I have, 3 of these 2+ charges, and 2 of these 3 negative charges, the result is that I'm going to have a 6 positive here and a 6 negative here, and that comes out to be 0. So this works out for us. So what we need to do is to take those coefficients here and here, this 3 here in front of this 2+, and this 2 in front of this 3 negative, and transfer them up here. Have a 3. You need 3 of these plus 2 of these to give us a particle or a resulting compound that has a charge balance, that the charges are basically wiped out, okay, or balanced out by each other. So the result is that we're going to have a formula where we have 3 magnesiums and 2 phosphoruses. Okay? So any one of these ways we're going to get the right formula. Okay? So what about the name? We don't use prefixes. This is just magnesium phosphide. That's right. You name the first thing what it is, or what it is on the periodic table. It's a magnesium ion. The phosphorus becomes a phosphide ion, negatively charged monoatomic ion. So this is monoatomic because it's one atom. It's negatively charged. Negatively charged monoatomic ions are going to have a name ending of IDE. So this is magnesium. We change phosphorus to phosphide. Magnesium phosphide. Okay? How are we doing? All right. So we're going to use, I'm going to kind of shorthand this a bit just for time. Orbital notation, electron dot formulas, and ion symbols to get the correct formula. I can write the word formula here for a compound of gallium and fluorine. Okay? So we're going to use orbital notation, electron dot formulas, and ion symbols to get the correct formula for a compound of gallium and fluorine. Fluorine. Alright, so when you get everything done, you're going to find there's a formula when you balance out the charges here, balance out the electron dots, or moving the electron dots around, when you move the electron arrows around, all of those are going to give you gallium fluoride, GAF3, and the name is gallium fluoride. Alright, and there's your homework. In the next lesson in this series, we'll be looking at more complex types of nomenclature for ionic compounds.